let's get started. First thing we're going to do is kind of do a very quick summary of the first two sections, and I'll show you what I have on, excuse me, what I have in Canvas as well. So these two are actually being covered before, but I thought it might be a good idea to just do a quick scan through. Our last chapter is differential equations, and I don't want to shortchange differential equation. They are a big thing. If you become an engineer, this is going to be your bread and butter. That's kind of how you're going to describe relationships and systems, and also how a lot of the equations that are used in engineering or electrical engineering or any kind of engineering for that matter tend to be written in the language of differential equations. Now, I'll give you another idea of why differential equations are big and important. We have one class devoted to nothing but Calc 1 and one class devoted to Calc 2. We have two classes devoted to nothing but differential equations called DiffEq1 and DiffEq2. So if you're interested in doing any kind of engineering, you've probably got that on your list somewhere. Certainly DiffEq1, but probably DiffEq1 and 2. So if we do two complete classes on nothing but solving differential equations, you can imagine how important they are. Now, my job is not to do 2 quarters worth of differential equations. So that's far too much to cover. What I'm going to do is essentially just give you a taster, an intro to what these things are. And so let's begin right at the start at 9.1. What is a differential equation? DE for short. DiffEq is another name for them. Well, a differential equation is essentially an equation that contains at least one derivative. It's as simple as that. And differential equations get their name from the highest order of its derivative. So here's an example of the differential equation. It's called first order differential equation. And that's because the only derivative is a first derivative. Here's one where a second derivative plus the first derivative plus y equals x squared. And this is called a second order differential equation because it has a second derivative in it. There are many, many, many types of differential equations, but we're only going to look at 2. We're going to look at how do you solve a first order differential equation called variable separable, which is what I'll start today, later on. And then after that, we'll be looking at linear first order differential equations. And they'll give you an idea of what they look like and the techniques that we're going to use to solve them. And as I say, I've got a whole video on this, so your job is to go back and look at it, and I'll show you later where it is. But continue with this then. What do we mean when we solve a differential equation? Well, essentially what we're trying to do, if I move this a little bit more, is we're trying to find the function y that satisfies the differential equation, right? We're trying to solve it. And so you take a differential equation like this, or like this perhaps, and you try and solve it in the form y equals some function of x. And if there's a plus c, you know, like the arbitrary constant you get in integration. And by the way, a lot of the solving techniques here involve integration. If you have an equation, a solution that looks like this, we call that a general solution. Because c could be 5 or 55, and each value of c gives you a slightly different answer. If, however, you know the exact answer, right? No missing terms, no plus c's, then we call this a particular solution. So here's a very simple differential equation. dy by dx is equal to 2x. The general solution of that would be any formula, any function in the form y equals x squared plus c. And that would be my general solution. And this guy here is my particular solution. So that's a kind of big picture view of what a differential equation is. Now we're going to look at a guy called direction fields. Has other names, but direction fields will do. What you imagine is that you've got a differential equation and it's first order and it's written like this, dy by dx, and it's equal to some combination of x's and y's. And what you do in a direction field is you visualize what that guy would look like. So I'll restart this fella. So you take little snapshots. For instance, if I take this point here with coordinates 1, 2, its derivative would be 1 squared times 2 would be 2. And so what you do is you draw a little baby line and you make it slope 2. And if you wanted to get this point here at 1, 1, the derivative would be 1 squared 1, which would be 1, which would be something like that. And if you wanted to get this guy here, which is what at 1, 0, its slope would be 0, and it would look like this. And you'd have one going like that, and one going like that. So you can imagine for all these different points, a whole sequence of little lines that look like that. And this whole picture, when it's complete, is called a direction field. And what this does is it allows us to visualize what this differential equation looks like. So it's a very specific diagram that essentially tells you at snapshot points, the slope of the line represents the value of the derivative. So let's show you what we have in Canvas so that you can go back and in the future look at these things. So this is our class. If you hit 152, for instance, you should see this guy. And if you go to week 10, here is a section dealing with modeling. And here's another one, tells you a little about direction field, and that will help you with your homework. If I then return back, I can show you this little fella, direction field plotter. So here is the particular derivative that we're dealing with. That's this one here. Let me kill some things here. I don't really need that. And what you can see if I zoom back a little bit, can you see what a direction field looks like at any given point? That if I could find the slope of that line, that would be the value of the derivative at that point. Now, if you take a point like 0, 1, and then you use this, what you would do is you go a little bit and then you take here, and that would go here, and then it would, well, you can't see it, but well, it would curve. Well, it looks like this one would curve in various signal. If I take this one here, let's suppose I did that, it would, I see what it's doing. Can you see it kind of ripples like a little sinusoidal curve? These direction fields are visualizations of this particular derivative, right? dy by dx equals that. Now, at any given point, you can draw a curve that would represent the motion. What I tend to do when I look at these questions is I imagine it's like a river current, and I drop a little paper boat at, you know, whatever the coordinate is, 3,2, 1,5. And then at that point, won't the boat follow a particular current? It will have a particular pathway. And each pathway is representing one of the possible solutions to that differential equation. So that's some resources for you out there, things that would be of help, I hope. And we're ready now to start 9.3. We're going to look at how to solve a differential equation. And the particular type that we're going to look at today and tomorrow as well is this particular situation here. Variable separable, section 9.3. Now, a first order differential equation that can be written in this format. Now, Notice how it's written. dy by dx equals a fraction. And on the top, it's some function of x, right? X cubed plus 1. And on the bottom, it's another function, but a function of y. If your differential equation can be written like this, we call these first order, because it's got first derivative, variable separable, which is quite a good name, right? You can separate the variables, differential equation. So let me show you an example of that type of equation. Excuse me. Now, what I'm going to do here is go through the key stages, the key steps in solving them. The first step is that you need it to look like this guy here. We need a fraction. And on the top, nothing but x's. And on the bottom, nothing but y's. Now, I'm going to put x squared on the top. Right? You see, it's still x squared. Now, algebraically, how could I rewrite this as a fraction so that it's still got the same value, it just looks different? And you're going to find that you're doing a lot of algebra today. Almost no calculus, one line calculus. Everything else is algebra. How could I write 1 plus y squared on the bottom and still be equivalent to the original?
Would you just make it 1 plus y squared all to the power of -1?
Yes, you could. And in some cases, that would be the right thing to do. But in this case, I'm going to write it slightly differently, although it's equivalent. Why do you think I'm going to write it as a funny fraction on the bottom? Why do you think I'm writing it like that instead of this, which is equivalent? But why this and not that? Any ideas?
Are you going to differentiate it into a tangent or inverse tangent somehow?
It is, yes. And how we're going to do it is step 2 now. So step 1 is, if you need to, which most of the time you will, write it as a fraction like this. Now, this notation is really helpful because it helps the next step. Can you remember doing a kind of crossover trick that we did before? I'm going to do exactly that crossover trick. Can you see the crossover like you did in USUBS, for instance? So what mathematics says is that if this derivative is equal to this fraction, you can do an equivalent algebra. In other words, this guy is equal to the integral of that guy. And basically, you do the crossover and then you stick integrals to have a meaning to it. Now, do you recognize 1 over 1 plus y squared? Because someone did mention it a few minutes ago. What's the integral of 1 over 1 plus y squared?
Inverse tan.
Yes. In this case, inverse tan of y. Sneaky. Now, when you solve the differential equation, variable separable, your goal, when you're finished, is to rewrite the information in a format y equals some function of x. Now, one of the questions that someone asked in the other class is, why does this one get the plus c and that one doesn't, right? Because when you integrate and it's a general integral, don't you have a plus c kind of thing going on, right? Well, let me try and explain why we don't need it. I could have written plus c1 and 1/3 x cubed plus c2. Wouldn't I have to call them different because they could be different average constants. Now, if I rearrange this, wouldn't I get 1/3 x cubed plus c2 take away c1? Agreed? Now, aren't these placeholders for numbers I don't know, right? Arbitrary constants. I don't know who C2 is. I don't know who C1 is. I certainly don't know what C2 take away C1 is. But isn't C2 take away C1 just an arbitrary constant? So it makes more sense only to have one of them, and you typically give it to the right-hand side, the X side. So that's the reason why this is plus C. And you're going to find later on that we do some weird stuff with this plus C. Let's continue with this, Helena. Since I want this to be y equals, that's what step 3 is going to be. What can I do here to both sides to find y? Think algebra. What could you do to both sides to get y on its own?
Tangent.
Yeah. So if you take the tangent of both sides, you know that rule, as long as you do it to both sides, it's okay. There you go. Step 3 is over. Now, there will be, but not today, a step 4. Now, step 4 will happen when you're given a differential equation and you're told something like y of 0 is equal to, I don't know, pi over 4 or something, right? Now, when you're given this extra, it's called a boundary condition. What you're saying is that when x is 0, y is pi upon 4. And if that did happen, this piece of information allows us to find out what number c is. So y is pi upon 4, and it's the tangent of c. And that makes c then the inverse tangent of pi upon 4. And so our solution would now be the tangent of 1/3 x cubed plus the inverse tangent pi upon 4. So that step 4 won't happen today, but you will see it tomorrow. We would finish on this line here. Now I said there's going to be a lot of algebra. There already has been. So here is our first question from the homework. And we have dy by dx is equal to this guy. Now I need to make this a fraction, and that means you got to figure out who goes in the top. X's always go in the top. How do you think I'm going to get that y squared down here? What am I going to turn it into?
1 over y squared.
That's what we did last time. But just to be awkward, it's going to be -2 this time. Can you see why -2 makes more sense when we come to integrate? But why 1 over 1 plus y squared made more sense when we come to integrate? So don't you have to decide on context? Because there's probably going to be 2 choices here, right? Sometimes negative, sometimes a fraction. Which one would make more sense? Right, in this case here, when we do the crossover, are we happy about the crossover? Right, now integration, power rule, add 1 to the power, divide by the new power, plus c. This fella, add 1 to the power, divide by the new power. Now we have to get this answer to look like y equals. That's our goal. Rewrite the solution in the format y equals, run this rather ugly way. I'm going to do my favorite, as long as you do it to both sides, it's okay rule. And I'm going to take it really slowly, because if I try and do too much at once, I screw up. I'm going to multiply both sides by -1. And no, that is not a mistake. But shouldn't that be negative c, you're all thinking? Well, technically, yes, but isn't negative c a number I don't know? So we typically just keep the damn thing as plus c, right? If I don't know what you are, minus who I don't know who you are, I still don't know who you are. Plus c is a placeholder for the number you don't know. So is that kind of weird algebra? Are you cool with that, right? Now, if you multiply c by 2, right, so you get 4x cubed plus 2c, you don't call it 2c. You just call it plus c again, right? 2 times something I don't know is still something I don't know. So you've got this funny algebra with c going on, which basically means unless you do something really weird to it, it's still going to be plus c. Now this fella, I'm going to rewrite like that. Can you tell me, Nan, what the solution should look like? How do I take a 1 over y equals this and get a y equals out of it? Any takers? How do you get 1 over y equals negative 2x cubed plus c and rewrite it as a y equals?
You're going to cross multiply, so it's going to end up as 1 over negative 2x cubed plus c.
Yeah, you can do it as a cross multiply. Couldn't you also just do it as you turn me upside down, you know, reciprocal both sides? I don't mind. I mean, people's brains work differently. I don't mind how you see it as long as that's what you get. And that's us finished. Here is our first homework question done. Yeah, let's try another one. We got a bit of a background thing going on here. Let's try question 2. Do y by dx again. 7x square root of y. You got to think of fractions here, and sometimes that means you have to write things down in a really weird looking way. But that's okay. As long as it ends up being a fraction, it don't matter how weird it looks. So you tell me what do you think the square root of y is going to look like when you stick it on the bottom?
Power of negative 1/2.
Yes. Now, I could have called it 1 over the square root of y, couldn't I? That was the alternate. Would you agree that negative 1/2 works better for integration in the power rule? Right, so you're going to have to choose sometimes between 2 things, which one makes more sense. Now we do the crossover. And now we integrate. Add 1 to the power, divide by the new power. Power rule plus c. Okay. The next couple of lines are basically to get this to become y equals. Small steps are safer. What do you think I should do to both sides to get it closer to the answer?
Divide by 2.
Okay. Now you might say, oh, well, I'll write a half c. Nope. Won't we do the funny algebra that a half c is just c? Right, it's a placeholder for a number I don't know. Halving it doesn't make any difference. I don't know if this line helps. I hope it does. If not, then you can pretend I didn't write it. What do I do to both sides to get from the square root of y to just a y?
Square it.
Right. And you gotta remember that this guy here is part of the package. You see that? It's the whole thing in brackets squared. And we're done. That makes sense. And that's our second one. Let's see what we can find for the next one. Oh, didn't take me long. Here is our variable separable. Oops. Almost screwed up here. Well, that guy does not look the way it's meant to. So the first thing I'm going to do is subtract this term from both sides. And the next thing I'm going to do after that is make it a fraction. Okay, who is going on the top, the numerator in this case? Who is the numerator, the top, going to be?
Negative 5x.
Okay. Now, what do you think the e to the y is going to look like when we bring it to the bottom, the denominator? And think integration after this, right? So think of the format that's going to make it easier to integrate. So what will the e to the y become?
Would it be e to the negative y?
Correct. Wouldn't 1 over e to the y not be very helpful if you want to integrate something, right? And if you get it wrong, you'll figure it out on the next line when you think, ugh, I don't like the way that's written. You can fix it then if you do that. Well, the integration's not that big a deal. Are you happy about the negative e to the negative y when you integrate this guy? You happy about where this little extra negative came from? Right, this guy here is just basically power rule. Now this fella here is going to become a y equals eventually. And so it's all algebra from now on. As long as the left-hand side only contains one letter y, right? It could be y cubed, y squared. As long as there's only one y, you should be able to algebraically rewrite it as y equals. Later on, you might get the odd 1 or 2 questions where this side is got at least 2 y's in it. Can you imagine a y cubed plus 5y kind of thing happening? In those situations, you can't fix it. So you don't need to worry about making it y equals. But as long as there's a single y, it is doable. I'm going to take it slow but sure. What do you think I should do to both sides next? And don't do too much, just one little thing at a time. What should I do to both sides?
Multiply by -1.
And that becomes positive. What will the c become?
Still plus c.
Still plus c. Are we getting less and less distracted by the funny algebra of c, right? 2c is c, minus c is c, half of c is c, right? Those things. Now, this fella, what do you think we should do next? What should I do to both sides to get closer to what I'm looking for?
I think Dylan had it in the comments. You do the natural logarithm.
We do, thank you for looking up that. I can't really see the comments, unfortunately, the way things are going. So if you take natural log of both sides, would you agree you get that? And, well, oh, that's easy to take care of. Can't we just multiply both sides by -1? And we are finished. So whoever suggested the natural log was bang on. It doesn't take too long for these questions to start becoming weirder and weirder. This is the first time we've ever had a variable separable question that looks as weird as this one does. And it superficially looks like you can't separate them. Right? So I'll give you a little clue. I want you to focus on these as two separate pieces. In particular, I want you to focus on these two. Is there anything you could do with combining these two in some way that might be helpful? T squared P, take away 5P. Anything that comes to mind that you could do with just those two terms?
Could we pull out a P?
Okay, let's see what happens. Sometimes you don't know what's happening. Okay, now I'll put a little bracket around that guy. Do you notice that this expression has a t squared minus 5 in it, and so does this one? Technically then, aren't these common factors? And that means that I can do a t squared minus 5, p, and there's only one of them. Sneaky. You see how that worked? I like these questions because they're just puzzles, right? There's, you know, each one's got a little tweak in it, a little twist in it. You have to figure out what to do. Now, that guy is good because if you can separate them as multiplications, can't you also separate them then into two fractions? Who goes on the top?
T squared
minus 5.
Okay. Now, won't this p plus 1 end up in the bottom? And we know there's two choices here. Isn't there a p plus 1 to the negative 1 or a 1 over p plus 1, right? That's the two ways we could go. Which of those two versions do you think is going to be most helpful when we go to the next line and integrate? P plus 1 to the negative 1 power or 1 over p plus 1? Which of those two do you think is going to be more helpful?
One
Probably
over.
the -1 power.
Okay, I was going to get both, so I'm picking that one, and then I'll show you what it would look like if I didn't do that one. Right, now when you do the crossover, you're going to get this guy. Would you agree 1 over p plus 1 is just a natural log, and isn't that nice? Right. Now, can you imagine that we went the other road? And it's okay, because if you go the wrong road, you can fix it later. Like we went that road. Then my crossover would look something like this. Right, and I don't have a problem with this fella, right? That's just a parallel. Do you see I have a problem with this? Would you agree that p plus 1 to the power of -1 is not really very helpful if you want to integrate? Well, you might say, well, you just add 1 to the power, right, and divide by the new power. Wait a minute. If you add 1 to that, don't you get 0? And 0 is bad news. So if you saw that, I hope what you would then do is say, okay, don't like the way that looks. Let's write it like this. Yeah, I like the way that's looking. So 1 over p plus 1, when you integrate it, is the natural log of p plus 1. This guy is a power rule. 5 is a power rule. And a c. Again, we should be able to finish this one by having a single variable p equals eventually. What would we do to both sides to get closer to that final place where that we want to be? What would I do to both sides to get that a little bit closer? Somebody in the chat? Let's see if I can find the chat.
Dylan said E.
Okay then. Raise both sides to the power of E. Are you happy about that? The E to a log cancels out and you get P plus 1 and E to the power on the other side. So I'm raising essentially both of these to the power of E. And on that side, this guy helps. Now, to find P then, and there is our slightly ugly answer. And if you got that answer, I'd be perfectly happy with it. Hopefully WebAssign will be as well. But let me just show you that you can do other things. If you have E to the power of various terms, isn't it essentially this guy times this guy times this guy? So I'm pulling out the E to the C and leaving the other two. Isn't E to the power of C just a number you don't know? So you could have called this, and it would also be correct. You could have called it that. Are we good with that one now? I'm happy with that, but just in case you're interested in, a different flavor of the same question. This will be our final one for today. We have dz by dt. Whoops. 4e to the t plus z equals 0. Well, the first step, I think, is pretty obvious. But the next step is less obvious. This expression, negative 4e to the t plus z, isn't really separable yet. It's got to be, t's on its own, z's on its own, right? You can multiply them together, but they have to be within their own world. They have to be separated. I can rewrite this guy like that. Are you happy about what I did there algebraically? The e to the t plus z is the same thing as e to the t times e to the z. Are we good with that? Right. Now, this fella, I can now separate into his fraction. Who goes on the top?
Negative 4e to the t.
Now think about how the e to the z is going to look when you put it on the ball. Your choices are e to the power of negative z or 1 over e to the z, right? That's your two choices. E to the negative z or 1 over e to the z. Which of those two do you think is going to play well with integration?
E to the negative z.
Well, I'll take z, but
Right.
right. And we do the crossover. If you integrate this fellow, you get negative e to the negative z. If you integrate this guy, you get negative 4e to the t plus c. You all comfortable about where that weird negative appeared? Okay. Our job is to make that thing look like z equals. Little steps, take care of little bits at a time. Okay, what should I do to both sides to make it a little bit easier to deal with?
Multiply by -1.
Okay, we've seen that a few times, right? So that becomes positive, and I think we should all be just comfortable now with the plus C. I think we've seen a version of this before, so hopefully it won't be too bad. The person who did it in the chat could jump in here. What would you do to both sides? I see at least a couple of nods, so I know a couple of you know what to do. Right, and the person in the chat has just said something, because I got one of my many windows, I put a chat window up, and you are right. You take the natural log of both sides, remembering that this is a whole package, right? And then multiply by -1. And here is our differential equation. There we go. Let me show you something. Yeah, we've got time. The rate of change of the population of a town at time t, right? So the increase in population is 3% of the population. So that would be a 3% growth rate. So there's a very simple differential equation. In fact, in a way, a lot simpler than you would expect. Now I'm going to call that 0.03, and that p is going to come downstairs, right? And I'm going to call it 1 over p. Are you comfortable about this becoming that fraction? Right, 0.03 in the top, and the p becomes 1 over p. When I do this fella, we get that. Now you might say, but there isn't any t there. It doesn't need to have a t, typically it does, but it has to have a value. In this case, it's just that decimal. The natural log of p is 0.03 t. If you raise both, oh, plus c, you get that guy. And if I rewrite this as e to the c, e to the 0.03 t, can't I call that guy c? Do you recognize that formula? Isn't that Math 141 exponential growth model? Do you see it was created from a very simple relationship? The increase in population is that. Couldn't you make it cleverer and sneakier and had death rate and immigration rate and a whole sorts of other things and solve that one and have more and more advanced population models? But that just shows you the power of differential equations. Set up a relationship that says the rate of change is equal to some function. It can have p and t in it, hopefully, and they're separable. And if they are, you can solve it. And now you've got a formula for calculating the population. All you need to do is find out who C is, right? And can't you do that by, you know, at time 0, the population is 500, in which case you'll be able to find out that C ends up being the initial population size. Okay, last name, and bye-bye. I'll hang